Adam Dupay here, and I am back for more live CTF challenge hacking. It's been a while. In the meantime, we had the great DEF CON CTF 2022 played in Vegas. One of the cool things, if you haven't checked it out, go check out live CTF. So they actually had one of the really cool things they did was had kind of a side event to the main DEF CON CTF Attack Defense CTF, where they had head-to-head hacking, so simpler hacking challenges. You can go see and these were live streamed and casted, so lots of really cool stuff on there that I think you'll definitely enjoy. You can check out all of the challenges here, who played who in the challenges, what the teams were. In the end, Team Starbugs won that. Really quick, really cool stuff. I highly recommend going and checking these videos of the CTF challenges. You'll learn a lot and be maybe wowed like I was and seeing these cool challenges. So we had that. I was on vacation and now I'm back. So now I'm back to streaming. So what I'm going to be working on now. So we previously solved the Insomniac One Right challenge. And what I'm decided to do here was there's actually not a lot of people out there that have maybe seen or attempted the attack defense challenges. So specifically what I'm going to try to do is go look at attack defense CTF challenges and kind of live hack and solve them here. There's a different way of thinking about them. So unlike a traditional Jeopardy style CTF challenge, there's not just one path through to try to exploit the challenge, but there may be kind of multiple ways through and multiple paths to victory and to the flag. So what I'm going to do here is, so here's archive.ooo is a website where you can, that we, as Order the Overflow created, you can go in and check out the challenges that we have here. I'll also, as part of this, as I go through and do previous challenges, I'll try to add them here as best I can. So, like most things in life, you got to first log in. So we'll log in here. What I'm looking for is the challenge called barb-metal. So this was a challenge from DEF CON 2021 CTF Finals. So inside barb-metal, so we can look at this. We can see that it's a reversing / pwn challenge. And it was an attack defense challenge, part of DEF CON 2021 Finals. You can actually like the points here are just internally to archive. Of course, this was an attack defense CTF, so you got points for exploiting the service over time. Cool thing is that we can actually run, let's do this so I can show this. So we can actually run this multiple ways. So we can, I have, run it with sudo. So I'm going to run and pull. So we can actually run this challenge completely locally. We can also run it, and we'll do this next. So we have a target to hit against of the OOO. So here we can now, need sudo. So now we can run the challenge and then get the that IP address. So now, now I actually don't know much about this challenge. So 7829. Okay, it's hanging. Let's try curling it. I think this was, yeah. Okay, cool. Awesome. Okay, so now we actually have this challenge. Sudo docker kill. So now we can run this challenge locally here against our local machine. We can also run it with the source code on our laptop, and we can run it hosted by OOO. So this will actually run the challenge and run the challenge for us on our systems. And if you want to, this is actually a cool thing that I'm involved with, is if you want to, you can actually opt in that your traffic that you send to this service will actually be used for research. If you don't click this button, it won't do that, so don't worry about that, and it will spawn this server for 20 minutes. So let's do that now so we can see what this looks like. So, oh, and the other thing that's important is down here, description. So let's see. So here we go. So here's the description in the game. So if you're playing this game during DEF CON 2021, you may have seen this. And what this says is OOO's new IoT platform, Ruby on Rails. No, Ruby on bare-metal x86. Interesting. Building native extensions. This could take a while. This challenge has no flag limit and could be retired at our discretion. Okay, and there were 2 downloads given, service and payload.bin. And so let's see. So I've already downloaded them here. So if we run file, we can see that, wow, that's a big boy. So service is 1.3 megs. That'll be super fun. I bet that's what we're going to have to try to reverse. And if we look at payload.bin, so payload.bin is something. File tells us that it is just data. Okay, cool. There's some stuff in there. So let's... The other thing I think that was implicit here that we should probably add to this description is I think the flag is in /flag. Cool. So here, finished. So it finished loading while we were doing that. And I think I should just be able to hit this in my browser. Let's tell it we want HTTP. Boom. So now I have my barb-metal instance. So this should be the standard thing that we saw there. So let's see, interface. Smart speaker is active and online. The thermostat says the night temperature is 69 degrees Fahrenheit, day temperature 78 degrees Fahrenheit. Almost getting hacked, almost certainly. Interesting. The IPs don't quite work here, but that's okay. So we'll figure out how to play with this guy. Is there? I wonder if this is. Anyways, okay, we can see here. Connect. Alarm, alarmed. OOO bootloader, waiting for 32 byte payload size, ready to receive 4590 bytes. Key import okay. Calculating payload digest. And of course, this is what's important is to just like understand and read the service. So that's what I'm doing here. And we can see payload digest. We have something here called payload.bin. So let's do SHA-256 payload bin. SHA-256 sum. Okay, that's different. That's interesting. Calculating signature digest, launching payload. Welcome to Barb OS. Not armed. Therm read day Friday. Therm read night Friday. Alarm, alarmed, not alarmed. Therm read day Friday. Disconnect. Okay, interesting. And we have a console here. So what if we just try typing these commands into the console? Does it do anything? Okay, and we may need some web stuff here slightly just to expand that content out. Let's see if I right click, click inspect elements so I can see that in here. Okay, so that was that input there. Could be getting updated. We don't quite know. So the next thing I'm going to do is use this network tab to view what's going on here. And the other thing I'm going to do is open this up in Chrome. So it's possible that the service actually works better in Chrome than on other things. So that's kind of a frequent problem with web applications nowadays, but that's okay. So what we're going to do is look at the network and look at all the network requests that our system makes. So first we make, it's a web socket. Cool. Okay, so we're going to have to learn how to use web sockets here. That's cool. So it makes a request there, the response. Now the other thing we always want to do on a web challenge, right, is we always want to look at the source just to see, and again, this is the HTML source that it's giving us. So it's telling us this URL, localhost 8581. Interesting. So this may mean there's another port that we need to talk to at some point. Usually most finals challenges have one initial port, but it could be that internal web server is talking to this 8581. So we just kind of scroll here. CSS stuff may or may not be important. Let's try to ignore it for now. Wow, a lot of CSS junk. Mostly CSS junk. Okay. And okay, icon, link, canonical, interesting. So thinks that it should be on localhost 8581. This could be messing things up, but we're not exactly certain here. Okay, so right link / barb-metal. Okay, this is where we got the barb-metal, the version numbers, the pwning, the getting hacked. This was the thing with plugins. So let's, since we see this link and we saw earlier that it's / plugins there. Here. Okay, Sinatra doesn't know this ditty, so this means it does not actually exist there. Interesting. So it's not. Okay, so we know it's a Sinatra web server. Could be useful, probably not, because this is marked as a pwn and reversing. Okay. Smart speaker, active, online, thermostat, night temperature, day temperature, alarm, disarmed, system information, DEF CON 2021, challenge, barb-metal. Okay, SVG stuff. Console, click, do something. Okay, cool. So there's JavaScript here. There we go. Helper function, log message to screen. Okay, so that's set up WebSocket with callbacks. So this is setting up the WebSocket, WebSocket on open, connect, disconnect. Okay, so this is what the output here is showing us is when we did, I think that's what this is. So this thing in here in the middle, connect, alarm, armed. So this is, calling this log function. So it's appending the message that it gets into there. And okay, new WebSocket, create. So it's making a WebSocket back. So that's definitely how we talk to it. So on a message, your function. These are great names. Your function, get element ID, commands blah, blah. Okay, these are the commands that it's going to run against it. Alarm armed, therma. So let's see, do something. BTOA is JavaScript for base64 encoding. So send B6, so send what we're trying to do, so log it. Okay, so the format looks like it's base64 encoding. I think I should have in here. So even just kind of looking through that, we should be getting, and where's do I have a WebSocket plugin here? Well, I bet it's really good with that. Let's see. Yeah, so this is cool. So we can see that so on a message, so when we receive message from the WebSocket, if we haven't started yet, then we call this function. And then we get, so a ASCII to B, ATOB. I can't remember exactly what that does. I know it's the reverse. So ATOB GIS decodes a string of data. Okay, so this is base64 decoding. So base64 decoding, log it, split it with spaces. If it includes not armed, okay, so this is where it's updating state on the web page. So it's checking barb-metal alarm, text content sets disarmed, armed. If it includes day, then it, whatever, messes the day or night temp. Then it logs the data that we get, and it also console logs. So if we open up here, we should see, so we can see a lot of the data that's flowing back and forth here from this connection. But I think the main thing here is what we're going to want to do is talk to this thing over WebSockets. Because I think that's what we're going to end up wanting to do. So did we do anything there? I think we're getting continuous stuff there. Let's see. Yeah, so we're getting a not armed, barb-OS. Awesome. Okay. So now we should be able to, so now we can talk to this thing, or at least we should be able to, right? So what we should be able to do here now is be able to make a WebSocket connection to this machine, and then we have a lot of the input and output. And I would bet that at this point, this is probably all we need from this web interface. Maybe there's something there. We did see the interesting thing about the plugins, but for now, let's ignore that, because what we're going to do now is look at the binary. So let's open up this binary. So if I can say disassemble a new file, and we are in CTF, old chows, barb-metal service. Okay. Popped. Okay. Information has been processed. Great. So it popped us into start. And I believe if we go back to our friend file, it would tell us that it's statically linked and it's stripped. So we don't expect to have any symbols. We don't expect to actually know anything about this. Okay. So then we can look in here. Let's see. Is that text large enough? Try to increase it. Font, not colors, because the color is obviously great. The font. Let's pop you up to 18. Holler in the chat if this is too small to read, and I can make the font bigger. Okay, so, but we have strings that we care about even here. Bootloader, waiting for received bytes, so this is good. One question that comes to mind is where does this these payloads come from? But let's look at okay, great. So v5, interesting. So this function is used a lot. It looks like puts like. Oops, that's not what I want. I want to say print like. So now I know that this is a print like function. Maybe at some point we can figure out what exactly it is printing, or how it's printing. It could be, yeah. So VA, okay, VA start, VA stop makes it feel like this is a printf function, and that whatever. Call something else, and I don't really care. I'm getting too in depth, so call it printf maybe. Because maybe it's printf, so it looks like it is printing out these strings. Maybe this is the socket that it takes. Not sure why it's including that 5 here. Let's see, subtract C, effective address. Oh, interesting. Huh, it's a weird way of doing that. Into EAX, we'll push that into EAX. C. Oh, the other thing we got to remember is we're using, let's see, using 32 bits, so we have to get ourselves back into 32-bit addresses, 32-bit, everything's here. Okay. Here's pop in here, see, okay, this does some stuff. Has some unknown chunk, does some stuff. We can kind of ignore. So what we're going to use basically right now is the clues of the challenge, including the strings that are already here, in order to try to understand some things about the challenge. Let's see what happens if I run it. Seg faults. Big seg fault because I don't have the right versions. I have no idea. Is it just executing? It said barb-metal. Maybe it actually is assuming to be like a bare metal thing, but let's ignore that for now. Okay, so printf. So this sub, what address of v0? Okay, so what we can do is use the context clues here. So this says waiting for 32B payload size. So 32 byte payload size. So this would probably be, or is it 32 bits? I don't know. I guess we'll see. But what the nice thing is, so we can know that this is definitely printf now. Why? Because this said receives %ZD. So print out as in as decimal. I think is Z. I think it's hex, but I guess it doesn't really matter too much. So print out the thing that we read back. So this is what we passed in the address of into there. So this is payload That's going to be the payload size. So we're passing in the address of the payload size here, 4. So that would be the size of an int. And then ready to receive that. Let's double check that over here. Oh, WebSocket is closed. Okay. Let's see. What did it say here? Waiting for 32B. Payload size. Okay. I think it's 32 bits telling us that the payload size. So I bet this is read 4 bytes. I bet this is read. So my thought is this is basically pass the address that you want to read into and then the size, so in bytes. So this would be read in 4 there. And yeah, so this says A1. So A2 is num2 read. This is the number of bytes to read. A1 is destination. So result, if not result. So if we're at 0, break out of this and return the results. Otherwise, this is V2. V3 is a pointer that we're going to point to V1. So we copy that there. This looks like a let's call it like get car. Because I think this is what this does. So it gets 1 character. Yeah, so V2. And then it sets that equal to V3. So I think this is probably just get car. We can pop in a little bit, but yeah, I think I'm totally fine not going into this function. And this is another tip. So we think we know what this does. Read in 4 bytes. Okay, then ready to receive this many bytes. So let's see. Interesting. So I'll call something there, but then it... Okay, great. So it does read into V2 payload size. V2... Interesting. Okay, so this would mean make V2 be our payload. I see. So payload, and this will be the type of this is wrong. This is basically a car pointer. So this is a payload. And what we're doing here is, I don't know why all of these change type. No, it should be. Okay, there we go. Now we're back to pretty types. So now we're going to look at launching payload, read. Okay, we're right here, yeah. So what is it doing? So it's getting some character pointer, right? It's allocating some memory. Or this must be a malloc. So it must be allocating payload size. So we said, hey, we're going to send you this much. It's probably going to alloc that much and then read it. So we know it has to read somewhere. So we know that this is a pointer that it's passing in. And it's going to read in payload size. And payload size is unsigned int. This is probably malloc. And yeah, that's good. Cool. So malloc takes in size. And interesting. Okay, so we probably don't right now need exactly the information about the size. Oh, let's run checksec on this guy. So we can understand. Oh, perfect. No railroad, no canary, no NX, no PIE, has readable, writable, executable segments. So that's great. Okay. So if dword okay, that's reference places in there. Okay, back here. If dword plus size is greater than dword 10,000, so one bad boy, one bad boo. Interesting. Okay. But I think this is actually the addresses. I think this is just saying if it's over, so it can't allocate anymore, basically. Okay. So this, my guess is, okay. So this must be the start of the heap. Okay, so it's probably just using a really simple heap where it just starts at the heap and it just starts giving chunks. So the heap start. Yeah, okay, D word plus equals the size. Let me check this here just to check that. Okay. This plus dereference into EAX. Cool, okay, so that is storing that memory there. Okay. So what I'm checking here is that, okay, so my intuition here is this is checking if we have enough to allocate. So interesting. Let's double check this. I think, so we could already see our first vulnerability here, maybe. This is this malloc. So what we passed in here from malloc, here payload size is an unsigned int. And in here, in our malloc, I'm going to change it to malloc because I'm highly confident it is. In our malloc, it actually has an unsigned integer. So what this check, let's see. The check here, oh God, size. So I think what this means is the size could be negative. So if we say that we're going to send a lot more data, a lot of data, it may malloc and we may be able to bypass this check. I bet we can trigger this assertion check pretty easily if we just send something that is beyond there. But basically, so I think this, so that is the most memory we can have. I wonder, is this? No? Okay. So, one bad. Huh. It's all zeros. This is interesting. Okay. But. Okay. So this is our. So this is like, yeah, our number in the heap. Why doesn't it have? It's the only places that it's referenced. Yeah, I guess. Okay. Plus equals the size. Okay, I guess this is the size of the heap. So this maybe is max heap adder. And this is current heap location. So yeah, this is just checking if that's greater than our max heap size. It's not adder, it's size, max heap size. So if this is greater than our max heap size, then say that failed. Otherwise, start at the heap, add to there, and that's what we return, and then we increment that by size. So this is an offset from let's say heap free offset. Cool, and that's going to return v2. All right, so we think there may be a vuln. Let's put a comment here. Okay, cool. Then I can go back to malloc. Okay, so we get the payload. So we read in the payload size into payload. And we can just check read really quick. Oh, we already did this. Cool, so that makes sense. 256, I don't know why that's there, but we'll see that. V4 is equal to 0. If payload size is greater than... okay, so if payload size is greater than that, interesting. Is that 256? Yeah, I think so. Yeah. So if payload size is greater than that, then do this, something to it. Interesting. I wonder if there's a bypass where if the payload size is small, it doesn't actually do anything. This may be checking. Yeah, let's see. Just pop in here really quick. Assertion failed. Assertion failed. Key import okay. Calculating payload digest. SHA-5256. SHA-256. Malloc some stuff. Okay. So this is good because this is where the other output comes in, but it's interesting because if we send a small payload, we don't have to deal with that. So let's see what this, if payload size is greater than that. So this must be verify payload. Ah, okay, and this is the, is payload verified? So if it is, okay. But we can't verify the payload here. Okay, I see. Launching payload. Payload pointer. Okay. And then invalid payload signature, launching backup payload. So this is the backup payload. Interesting. So stuff in here. So we could probably extract this and figure out what, and send this as our payload. Although I wonder if we'd be able to. We really are going to have to dig into this thing at some point. But let's see. Okay, so this looks like, oh, interesting. Huh. So based on the variable names, interest change priority, TCB, mutex, going back to our challenge description, new IoT platform, Ruby on Rails? No, Ruby on bare-metal x86. Hello. So we do know this is some kind of Ruby on Rails thing. Interesting. MRBC init alloc. What is that? Am I a hacker? I like to think so, but no, I think people would agree. Okay, interesting. mRubyC ESP Arduino 3. Okay, interesting. So it's doing some stuff. And then the interesting thing is where it passes in our payload pointer. So, so this, let's call it a, and then it should be a payload. And the second thing that it gets passed in is null here. Oops, don't want to go there. Okay, payload A2. You sure? Can you hack my Instagram? No, that's illegal. I don't do that. Okay. These look like asserts, all of these. And I'm going to Google for this because this looks like something that is present in some code that we... Nope. Interesting. I would have figured that would hit for something. Okay, let's try alloc.c. What we're trying to do is figure out this place. mRubyC. This looks promising. Where is the alloc.c? Okay, there's alloc.c. Looks like there should be a function called mRBC. Here's our function. And block size target. Block size target greater than or equal to alloc size. Okay. Question. Are you a programmer then? Yes, I am a programmer. I'm also a professor of computer science. I teach programming. Okay. First, check only the beginning of... There we go. Assert. Awesome. This is exactly what we were looking for. So this means that this functionality comes from here. This also means, man, I wish I should probably at some point figure out a way to write this, because this is for sure assert. And the nice thing in... Good. Yeah, I can teach, I guess, a little bit. So there's somebody out there that I've taught. That's cool. Okay. So yeah, what this is saying is, and actually, let's see, 538. So I could actually see that this is interesting. I wonder why those don't match up. But there's an assert statement that gives the programmer some, or gives the developer some information here. So when this assert fails, this is how it knows what the assert was. So this is why that is in here, this block size target greater than or equal to alloc size. Alloc.c is the name of the file that we're in, and then mruby raw alloc. So the cool thing is I can go here, call this mruby raw alloc, and then I can say this is and should be an unsigned int. Let's call this a size. How long to become a programmer? Good question. It all depends on how much time you're able to put into it. I think nowadays there's a lot of stuff out there that you can get into programming pretty quickly. And so, yeah, I think, there's lots of good tutorials. I would start with Python. Python's a great language to start programming, and that can definitely get you on your way. Okay, so let's call this something like execute payload. So payload, let's see, if this is Ruby stuff, where's payload going to here? If irep lvar end. Interesting. Okay, irep. So this looks like Ruby bytecode. I wonder if this is this Ruby engine compiled to bare-metal x86-64, which would make a lot of sense with the description there. Huh. Okay. So... Okay, key import. Where is this bytes coming from? Is this coming from us? Do we send this? Waiting for. Ready to receive. I don't think we actually sent anything, but maybe. Let's check back in the code here. Can you really make money being a programmer? Yes, you definitely can. I used to be a programmer once upon a time. I used to work for Microsoft before I started my PhD. And yeah, there's actually a lot of money in programming. I have friends who are my age who make a good amount of money by programming. Okay. Okay, my question now is, so okay, let's do this. Let's set up WebSockets. First, what I want to do is just check WebSockets. How can I do something quickly to talk to the WebSockets? Oh, I wonder if this is still running. Nope, it's definitely going to be dead. Okay. Okay, the instance on archive.oo got killed. So let's... Okay. Killing that container, dname. Okay, and okay, so this is the local IP address, and that is port 7829. Okay, great. That's all of that. So this will continue to run, which is excellent. And what I really want to be happening is to hit it from this machine. So that's right. I'm in my new window. SSH. There we go. Local machine SSH-D. So now I'm actually going to use Firefox because I set it up to proxy and I'm proxying my traffic. I should be proxying my traffic through there. Let's see. Proxy. Preferences. Yes, these are all of the exciting, super exciting parts of hacking. Okay, great. So now I'll use the SOX proxy here and I want to go to that IP address. And I set the port 7829. Yes, I know it's not a secure connection. Oh, I see. It's HTTPS. Yeah, there is no HTTPS here. Okay. Cool. So now I have the instance running, and now what I want to do is just connect to it with WebSockets. WebSocket SOCAT. That sounds interesting. Cool. Okay, install. Try downloading it. Oh, fun. Okay, so now I need to talk to this thing. So I'm going to do, of course, what you should do and just download some random binary from the internet. And let's see, Linux, Android, x86, 64, unknown, Linux. And I think copy link address. The number of tabs. Oh yeah, seriously. I always know I've done a CTF because I literally will have just hundreds of tabs opened. Because just like this, you need something, some tool, so you open it up, you look for it. This is because what I want to do here is I really want to just try talking to this service. So if I can't talk to it, so eventually I will write I'll write code to talk to it. But for now, I just want to mess around, and it's hard to mess around. Okay, great. It's base 64 encoded data. So what I'm doing right now is I'm trying to break. There is a CTF challenge. Where is it at? Called barb-metal. So this is some challenge that's running what looks like a website, but really this website seems to be just talking to a binary. So I'm trying to identify vulnerabilities in that binary so I can exploit that service to get access to it, get a flag, submit it here for points. So this is basically just like practicing security and getting better at cybersecurity. Okay, these are all, if you can't tell, anything that looks like this with equal signs at the ends means that it's base 64 encoding. Okay, so let's do this in Python. Python. Okay, WebSocket client. That's what I want. Okay. On message. Oh, okay. Short-lived. Okay. Communicate a message. Just click immediately when done. For the rest of the response. Okay, from WebSocket. So this is some library. So now I have to figure out what library I want to do. I'm not going to call this xplot.py. I'm going to call it like talk.py because I'm going to now write code to talk to this server. So we're going to need import base 64. And the other thing I want to do is increase the. I can never remember the keyboard shortcut to increase font size. Okay, set fonts, Control X and Control Plus. Okay. There we go. Okay. So let's go back to this example code. Cool. So what we want to do now is just do something to talk to it. Guess so on message. So how do I send data? More examples and examples. Oh, cool. WSDump.py script and the examples. Cool. So this is exactly what we want, this WSDump script. So I'm going to start here. But the cool thing is, why this isn't going to work is because exactly what that other program doesn't work is because it's just going to send me the base64 decoded output, but I need to base64 decode and import encode when I send stuff and decode it when I get it back. So I am going to just yank this code. Okay, so this is the WebSocket. So I'll need to install this library. I'll do that right now because this is this library that I'm using. So WebSocket client is what I want. Sudo or pip install WebSocket client. This is actually a good one. I should probably just have this installed since a lot of stuff talks WebSockets. Okay. Get encoding. Ooh, interesting. Huh. Encoding, not okay. Well, I don't want raw encoding. All right, let's just see what this does. So I yanked it from here. It's telling me I should just be able to do so, just like I did before. Python talk.py. This is the WebSocket URL. Okay, great. So we can actually see the input output. Oh, nice. It actually color codes everything. Okay. So, okay, raw input. Interactive console is actually what I want. Okay, there's the data. So I'm just going to be super lazy, and because this is the interactive console, I'm going to say I need the base64 module. Okay, so b64 dot, I think it's b64 decode. So to decode that as base64 data. And I think that's correct. Okay, so let's just try that. So this should then decode the data coming to us. Can only concatenate string, not bytes. Okay, so this is sending us back, oh, bytes that we need to, man, I always mess up which direction. So this is a byte and we want to decode. Hey, there we go. So it's telling us, oh, bootloader, waiting for 32-byte payload size, ready to receive 4590 bytes, key import okay, calculating payload digest. Great. Okay, so that's that. That's that. Welcome to barb-OS. Barb-OS. And if I say something, it will probably bork because it's not base64 encoded. So now what I need to do is, so this is read. So with this interactive console, I am going to see raw input, send base64 encode. Let's try that. Oh, we actually know the commands, so I shouldn't just guess here. We can say things like therm read day Friday. Okay. Let's see. Okay, that did not work. Let's see why. Okay, B64 encode. It's raw input. Raw input. Question is it strings or bytes? Maybe there's something going on there. Okay, there's again something results. Okay, so raw input. I hate these stupid sites. I want the actual Python documentation. And Python 3. So weird. Yeah, it is Python 3. Okay, raw input Python return string. Okay. Well, I don't know what I'm doing. I can just check. Okay, IPython. Hello. Oh, there we go. Okay. So I see this is using this raw input function, which should then encoding not equal to UTF-8, it's instance encoding if is instance line string. What if I changed raw input to input? I think the problem is it's actually calling this raw input, so it's not the Python. I was off track. Like it's not the Python raw input function. It's this function here. Yeah. So I think here this is a line. It should be a. Oh, it is bytes. Okay. So that's good. If args rar. No, I want. Okay, let's make sure we're actually calling that. I think that should have worked. Hello. No, it does say press Control C to quit. Okay, so now we can do a cheap debugging technique of making sure that we hit here. We can do import IPDB, IPDB.setTrace. This will trigger the debugger right here. Hey, there we go. So it's gonna say, oh, that's interesting. Okay, so that should definitely be okay. That's message console.read. Oh, a better way to debug this will be to do something like this. First, get the so this will let us input, let us debug better. Okay, result is equal to base 64.b 64 encode. Okay, that should then, yeah, return a bytes object. Now we can inspect everything. So now this will be better to debug. Okay, so what I wanted to send was, because I want to figure out how to talk to this guy, not armed. Okay, so now I can look here. I can say, what was the input? The input was not armed, P result. Cool. If we return result, cool. Okay, then that seems to be working, but why is it not talking to us? Why won't you talk to me? Okay. So now we can go back to this code and figure out what is going on here. Why it's not... Okay. Let's see. Firefox web. So now we want to look for how do we... Ah, there we go. Firefox new WebSocket inspector. Cool. So now inspect... Oh, wow, this is a lot. Okay, so network said WebSockets. Refresh it. Then messages. Ah, that's what I was missing, I think. Showing details about the... Let's see, clicking the one-on-one request opens a familiar sidebar showing details about the selected HTTP request. In addition, the UI now offers a fresh new messages panel. Where are you, my messages to? Where is this from? 2019. That's what it should be. I get cookies, request, response. Ah. Okay, so this is what I'm sending here. So the question is, so the first, Okay, so this is not armed. So then let's look at the code and figure out where the heck that not armed is coming from. Or where, I know it's in the script. Let's see. Okay, great. So commands. So the very first thing was like our function here. Blah. Oh man, this code is great. Okay, blah is 2. Okay, so let's refresh this page, get here. Commands. Ah, I think. Okay, so this is interesting. I think, why is it downcasing it? Something is down. I don't know, maybe we did it right? I don't know, but I think we need a /n at the end. I think it's reading until a /n or something. So maybe the raw input is actually not including a /n here. So let's try that. Okay. Because I believe if we do commands. Oh, obviously I don't want the /n at the end, but yeah, I think each this is what's happening. So each input that I'm giving as data as a new line is not actually get interpreted as a new line. So what I need, I believe this raw input, yeah, let me, I mean, I can go back here and just debug it just to double, triple check, which is always a good idea before you make assumptions. Okay, so this is the input. Oh, yeah, so there's no new line there. So plus. Okay, now if I tell it to arm yourself. Okay, well, I have 2 new lines. That's not great, but there we get the prompt again. Okay, awesome. So let's get this out of the way. So now we can talk to it, and this had a breakpoint on it. So let's get rid of that. So things just flow, flow, baby, flow. Oh, I see. It's not actually showing. Ah, there we go. Alarm armed. That's not what I want. What I want is you guys. Yay! Now we can talk to it. Awesome. So now we can say, ask it if it's armed. It's not armed. Read day Friday. Okay, so interesting things that we note from here. So just like this payload is actually coming from somebody else. I don't know exactly why this bootloader, this payload that it's getting, it must be reading from somewhere. I just don't know where it's reading it from. I thought it was from us, but maybe there's a way we can upload our own payload or something. So if there's a way, so, okay, the next thing to do is then now we can talk to it. So now we can, we know some of the commands, we know not armed. So now we need to figure out where in the binary this stuff is. Although it could be, you know, it's a highly distinct possibility that it's actually in the Ruby code itself. So we know some, we know like therm, read day, Friday, read day, what if I said Sunday? Read day, debug, illegal day, invalid day. Okay, cool. So this is giving us strings. All I'm looking for is some strings that we can look for here. So let's look in here. So we want that nice strings view. Okay. Okay. I don't think this is in here. Oh, there we go. Invalid day. Cool. Ah, it's in the, I believe this is in the default payload that we were looking at. I don't quite know. Just a sec. Okay, so I don't quite know where that is. Yeah, so this is our, some part of our payload. I wonder where, huh. Okay, there's pointers to it here. Okay, let's look at our payload.bin that we had here. Oh yeah, okay, cool. So gibberish stuff, irep, beep beep, therm, info, alarm, speaker, help. Try reversing it, a nice helpful string. I wonder if that's what it says when we say help. Let's look at it. I would bet if I was this person, that's what I would do because it's pretty funny joke. Okay, talk. Help. So the help just says try reversing it. Alarm. Info. Okay. Barb OS V0.0. Number devices 3. Last used device smart speaker. Okay, so therm, info, alarm, speaker. Oh, speaker foo. Let's see. The other thing I was thinking about is if any of these inputs. Alarm. Alarm. Alarm arm. Can I arm the alarm arm? Oh, I did. It said not armed and armed, so I can arm an alarm arm. Okay. Sunday, Monday, days of the week. We have stuff in there for that. Oh, good. There's classes. Looks like thermostat, smart speaker, do alarm, puts, print, debug. Cool. Those are in there. Split. Okay. Set thermostat. Okay, so you can set a thermostat. Puts debug. Playing. Oh, we can play songs. Oh gosh. Okay. Cue popular. I was looking for anything that would allow us to. Okay. Barb OS. Yeah. What I'm curious and wondering about now is obviously this help is no good. So this payload bin service. Okay, but every time we talk to this, it spins up with its own, let's see, its own bootloader. Yeah, so it oh, let's check if this is the exact same file size. That actually would help a lot. 5490. Why is that 1 byte different? Oh, that's really annoying. Okay. Okay. Let's start digging into, so now we know how we can talk to the service at least. Let's figure out this guy of how to yeah. I wonder where it's getting these things, but let's check. So yeah, those are functions we didn't dive into yet. So this looks like we're in a Ruby interpreter. So there's a couple different directions to go from here. And if I was on a team, I'd probably talk to my teammates to figure out, okay, can somebody start reversing this payload like this? I don't know if this is, if I can just say Ruby. Yeah, I have no idea if that's correct or not, but maybe if this is the payload, if we can extract the Ruby bytecode from this payload, then we should be able to start executing it, or maybe we could do with this backup payload or something. But what we can, so there's interesting things that it maybe sets up here. I don't know exactly what it's doing here. Oh, this looks like a mem copy though. A1 plus I is equal to A2. Oh, this is mem set. So this is, oh, interesting. Okay, so mem set. So this sets a memory region to a certain value. A2 is the size. Oh no, this is the val. And A3 would be the size. Cool. So this is clearing all of this, clearing this memory region, it looks like. From here to where? From here all the way to, okay. It's a lot. Okay, it looks like it's just wiping memory, but what does this guy look like? Read. Huh. Okay, so reading something into there. That's weird. Okay. Maybe a key or something? Hmm. Okay, key maybe because we don't know what it is, but where would that be used? But anyways, okay. So it's definitely reading 49 bytes from there, but that's okay. Maybe it's pretending to read a bootloader or something. I don't know. So reading that into there, we've got all that. V1. Okay, so now we need to see is payload. So verify payload. We don't know what that is. We don't know what that is. Something. It's D word. 124 hex. Okay. Pass in payload. This is probably maybe what? Payload start. V1 is set to 256. Oh, interesting. I wonder. Huh. Well, let's see. Okay, so this is something, this is always 256. When this sets the payload pointer into the, so, okay, let's look. I think I can use head. So prints all but the last num bytes. Print. So what I want to do is take the, oh, tail, duh. Okay, so man, tail. Output the last num bytes, use SC to output starting with num byte. Yeah, okay, so what I want to do is tail dash, let's say C. Yeah, dash C plus. Tail dash C plus 256. Payload.bin, bytecode. Oops, and we'll pop it into there. Damn. I thought this would tell me that it was, what's Ruby, okay, let's check it out there. Let's just verify that we actually did 256 bytes of that input. So I'm going to do the payload bin, type that through less. And so it should be AC04FB. Nope. Okay, that's because my plus was off. Starting, so what? The last output starting with byte num. Ugh, is tail dash C plus X plus what I'm looking for is tail dash C plus 0. Okay. Man page. Line delimiter. Tail print last. Okay. Last n bytes of a file. Okay, that's not helpful. All right. Let's just fuzz it real quick. I mean, fuzz quote in quotes 256. So I need one more byte. Let's say 257. AC04FB. So now I can say file. Okay. Let's see. Can I just execute Ruby bytecode? Oh, I remember I did this for a CTF. Anyways, I think I can do this with a little Ruby script. But anyways, okay, I just want to check if, because this is definitely going in 256. So that should be the start of the payload, right? 100. I did that right, I think. That math in my head. Oh yeah, that's why it won't just do it. Okay, cool. So I think that is the bytecode of that file, this payload.bin. We could also extract, the interesting thing is we have another backup payload here. Oh, this starts with write 0006, then mats. But maybe that's just a weirdness. I don't know. Could be important, could be not. Let's see. So let's check the verify payload. I have no idea what this is. Maybe some key or something. But let's check here. Okay, so the first thing we need to do is map this with what we know here. So that is our payload. So the third argument, I wonder if I can just, oh, I can change the types here. That is very, very handy. So that's a character pointer. That's going to be, I think, the start of the payload. Maybe it's like the signature. Maybe the signature is the first 256 bytes. That would make sense to me. Okay. Since I don't know what those are, I'm just going to give them names. Okay, and what was that last size? Was oh, this is the size of the second part. Interesting. I wonder if you can make this wrap around. Okay, This is line of. Yeah, I just want these to have the same names right now. Okay. If not, let's see where this is. Huh. Okay, this is in what .data? It starts at 0, so this must be some like already loaded check. Okay, Q mem copy D4U. Interesting. I have no idea. D4 unsigned from this. Okay. libtom math. What the hell is libtom math? Again, new tab. Okay, don't know what that's for. And this offset there. Ah, there we go. Cool. So again, we have probably what's like another assert statement. So I could say crypt register hash. Oh, libtom. Okay, cool. So this is libtom shit, it looks like, or stuff. I can actually check it in here. It's in. Why don't I have source in here? Source. Wait, yeah, what? Okay, that's libtom math. Oh, it's libtom crypt. Yeah, okay, there we go. Source. misc. Crypt. Crypt. Register hash. Cool. And it says hash not equal null. LTC arg check. Awesome. Okay, so the interesting thing here is just call that assert. And now we know this is register hash. Ooh, and the other thing we know is that it is a. So we also know that this is some structure. Ooh, that's annoying. Okay, so it may or may not be useful, but we can always just have this here for now. So now that we know that this is here, we can actually just kind of one-to-one map this. So yeah, it's arg checking this if hash. So this would be, then we should definitely update this name since we have it. Hash. If not hash, then assert. Otherwise, do this. And we actually probably know. Let's see, this is a while one. If pop. Mem copy. So we have this mem copy here. I don't know what these function calls are, but I don't really care. So this is doing register some hash. Okay, cool. And I would bet that. Yeah, cool. So source. Okay, great. So this is some crypto BS again. Very nice that all this stuff's in here so we can know to slightly ignore it, but also. Okay, so yeah, let's see. Source PK. I just like it since I'm here to add the function name since I can very easily find them here because we know these asserts. I know these will be the exact assert statements here. So RSA import. Okay, and in. Well, the other thing I can easily do is say in. That's in. This is key. This should be. There we go. RSA import is my guess. Yes. So there's this LTC arg check, which was that exact thing. So we know this is RSA import. This does actually look to be useful. Maybe there's some crypto stuff we can take advantage of, which would be cool. So we know arg1 should be in. We already have this as in. And this should definitely be, if it is in, it should be the character pointer, and then this says it should be in side long. And then a key, some RSA key pointer. Okay, cool. Oh, interesting. So this is some LTC mp.name. Huh. Let's see. Cert 0. Oh, interesting. Wonder why that's not just in here. It should be LTC_mp.name. Yeah, this is not bytes. This should be string. Yep. Got it. Got it. Okay, so this is LTCMP. So this is some struct. Then cool. Okay, and we could probably even look at this a little bit more and see where key is used. This, okay, RSA init. So we probably don't need any of these because we can probably stick to the top ones. But hey, since we're here, this was probably calloc. No, temp buff length. This looks like a big guy. In length. Temp buff. Address of temp buff. Yeah, okay. So this, anyways, I could keep doing this, but I think we're fine here. We don't really care. I don't think that there's any my intuition is there's no vulnerabilities just inserted magically into oh, I see, because it's a user call, so it's using that's interesting. So okay, I don't quite know how to fix that to make that better, but that's fine. We know this is an RSA import, and we know in so that's what's being, okay, so that's the payload we're verifying. So in, okay, the packet to import from, its length in octets. So this should be lang, I guess, packet. So if this is RSA import, this would be in lang. And this is the RSA key. Cool, this must be what it just has to pass, but so let's see. Import multiple formats of RSA public and private key. RSA public key or RSA private key is defined in PKCS number 1, v2.1, 2 prime only. Subject public key info, formatted public keys. Okay. So these are the ways that you can submit it in. Okay, so if we look, I bet these came from, yeah, so this is some, at what point you decide you may have gone too far in a certain rabbit hole and pivot to a different lead. That's it's honestly a great question. It's something that I'm still learning. I for a long time would go super too deep into CTF stuff. Actually, this crypto stuff is a perfect example. Because when I first started CTFing, I was almost exclusively a web guy, so I did web stuff, even though I knew binary stuff, but I focused on web. And so when we got to DEF CON finals, it was basically the only challenges I could even, there were almost 0 web challenges, kind of just like there are today, which is funny why people complain. But I spent probably like 6 hours on one challenge, just like getting super deep into IDA and reversing things before getting to a point and then realizing, where I even talked to somebody and realized, oh shoot, what I was reversing was the backdoor that the people had put in, because it was some crypto stuff. And I thought, oh, maybe there'll be some crypto bugs. I got really deep into there and then finally realized, oh shoot, this is just crypto operations that the organizers intended to put in there, but didn't have any like known bugs, and specifically didn't have any bugs. It was their backdoor that they put in so that they could do their crypto stuff, and only they could access that functionality. So that was a good hard lesson of getting way too deep into a rabbit hole of a CTF challenge. So um, what I'm and I always try to think about goals, like, right? Like my goal right now is to get an overview of how this thing is actually verified. So I don't want to go too deep into, oh, this crypto, especially because I know now that this challenge uses this library, so this libtom. So it's highly unlikely that they would use a library if they were going to inject a vulnerability there. Usually what you do is write it from scratch so that it's custom. And so, yeah, now that I just want to learn enough about something to say, okay, do I know kind of at a high level what this behavior is? And then you can really dig in when you need to be like, okay, where are the potential bugs and vulnerabilities? Okay, so here, this was I think our public key. Um, uh, yeah, so this here, if I Oh, okay. So I know what I need to do. I need to specify this as an array. So I can take this length here. This is 124 hex. That's the length that's going to be there. So what I can do to get a prettier picture of what's going on here is I can call this, instead of that, a car array of 0x124 bad declaration. Oh, wait, say type, can't remember the syntax here since, there we go. Okay. Okay, that didn't seem to help. Oh, I see. 3H0, 82, 1, 20, 30. Oh, this must be some binary format. I see. Interesting. Okay. I guess it doesn't matter. We could extract this and play with it, actually. Let's try that. Oh, there's something interesting. SHA-256. Interesting string. Okay. Okay, cool. There we go. And I think if I click from like here to here, let's see, you can file, let's see, export data. So I don't want it to be a string literal. Yeah, I think I can. Cool. So see, I can output this in a lot of different ways, right? I can do this can be super useful to throw into a C program. Really, they should have an option for a Python string, but that's okay. We can be super lazy here. Copy this hex string. Can do pop IPython. And I can say boom dot boom, 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 boom. I can never. Oh, I think I can do this. Bytes dot. I think it's from hex pub. There we go. So now that will, yeah, turns this, so 30 into there, 03 into 3, so we can verify that this is right. So I can just say with open pub writable bytes, as f dot right, and then I can say there. Okay, so now I have that pub file, and I can just verify that, I like to verify that my types and my sizes match. So 922 is a hex 124, which sounds good. And this means that this should be, so now what I did all this was just run file on it. Okay, great. Doesn't tell me that it has a file type, but I believe this is the burned in private key here. Okay. Okay. Great. Okay, and then we wanted to verify payload. Okay, so we registered the hash. We then imported, what was the last parameter of that import? RSA import, this is the key. I think that's the, destination for newly imported key. So this should be like the imported, key here. And the assertion failed. Great. Okay. Oh, and the other thing that kind of to go back to that question of like, how do you know when I've gone down certain rabbit holes? The other key thing is these strings that I'm seeing here, key import okay, calculating payload digest, using these printf functions. I believe that's, those are code that was written for this challenge because that is a standard format. It's what we see when we talk to the service, right? So we see waiting for this, which we know was in the start, which was likely written by the author. And then the key import okay, calculating payload digest, all this stuff comes from the from this function in here. So that's why I think understanding this function is really important because it's not part of a library. It's probably written specifically for the challenge. Okay, cool. So checking that the import was successful, that this RSA key was properly created, and then says okay, then calculating payload digest. So let's see, what were you used for? V. That is the first time you are used. Interesting. Well, that looks like something we could deal with. Okay, cool. Oh, this is probably, let's see. If I were a guessing person, which you do have to be a little bit of to do this kind of stuff, this is going to be usually the way you do hash functions is you have to like initialize them, add content to the digest, and then do it. So that's, I bet, what's going on here. But we can just look, SHA-2, SHA-256. Let's see, and I want something called MD. There we go. Yep, perfect. I was right. So this is going to be hash init. Oh, SHA-256 init. This is going to be MD. The hash state, which doesn't matter. We'll just call it I think we'll just call it a character pointer. And yeah, okay. So this just initializes the state of the hash. So if we go back, we should then see this makes sense. So this is some MD. Now the interesting thing here, so this is on the stack. I believe it's a large. I believe we're using the actual stack for this. So that is interesting. Rather than like allocating some memory, this is going to be this hash state. So depending on what size that is there. Oh yeah, here we go. Character, hash state, 406, perfect. Then that makes sense. Yeah, so why'd you go there? Cool. So yeah, this makes sense. So this is using, so essentially, so we know it's not actually a character array of 406. It's some structure that it's using to keep the state here. And actually, I bet we could map these values here to there, but probably don't need that, although it is interesting. Maybe if there's some overflow or something of some other value into the hash state, that could allow us to trigger a bug. Something to think about. Okay. So let's look at that. So init hash state, this would probably be into payload. So we're hashing the payload itself, is my guess. So yeah, so this is going to be in not equal to null. This should be process is my guess. So let's check that out. Oh, weird. Okay, so they're using some stupid thing here. Process a block of memory through the hash. Yeah, so this is going to be, I'm gonna not care about this too much. No, not type, but shop process. And then at this point, then usually call done. So this is probably going to be SHA done. So we pass in our hash state, and then we pass in the out where we write the output. And then, okay, which makes sense because now we're printing that out, and then okay, so this is 32, so 32 bytes. We just want to make sure there aren't any overwrites here. SHA-256 size, I don't remember bits, so it's, oh, good, it's 256 bits divided by 32 is bytes, so it's 8 bytes output. So now this is interesting. So we're using a different printing thing. Okay, so this prints it out, each of these values with %02, so this prints out the digest as we expect, and that would be here. Okay, and this is going to be this resultant size. The size is greater than A2. A2 is going to be the size. Okay, so this is not, obviously not this. This is a character pointer. Cool. And perfect. Okay. So then this basically is like printf hex hex string. Yeah, and it's definitely going to be used down below, so it didn't seem like there's any vulnerabilities there. Then print out a new line. Okay, then we do something else with SHA-256. That's kind of interesting. It'll probably be something, crypt find hash. It's weird. Why would it do that after it already knows that it can use the 256? But let's just quickly look at here. Source misc crypt find hash. Okay, this is exactly like it sounds. Return int, char pointer. Okay, find hash. Okay, so that's a hash number, and then this is probably looking up. Okay. Interesting. I guess what's the, okay, so this is, calculating payload digest, calculating signature digest. Oh, okay, so are they both the same? That's weird. Okay, so the payload, right, was the second part. So this will be definitely, it's not indexed into payload, right? Because that was the same part that we just shod where it told us that this was the payload digest. And we know this is what we actually execute. So this is for sure the payload. Okay, payload and payload length. Okay, and then that is V12 here. Okay, signature digest, great. Now the question is, why the heck is all this stuff in here? So the other trick that is really helpful to use is when you see random constants like this in here, Google for them. Because it's highly likely those are related to some crypto operation or something. Huh. Where? Okay, hashes, SHA-2. Okay, that's weird. Wait, we did this? Okay. Process. Yeah, okay, process done. The state here. Okay, this is weird. Okay. So this is how you should do it, right? You should calculate the payload, calculate a hash using some function. So this all looks fine. Now it's finding the hash. It's turning the hash number times 256. Okay, these are all the different digests or something. Hmm. Okay, and then RSA key. Okay, so this is the key. So we'll call it malloc. Okay, so now we length the start of the payload. So now we are creating something from the front of the payload. So malloc. Okay, I think this is what we said. What we think is this is the digest. So let's call this. Okay. Okay, digest and digest length. So we malloc something with the digest length. Okay. It's a character pointer. Great. Okay, so digest length. It's copied around. Ah, okay. So D word. So, okay, this is crazy. So it's calling into. Right. Okay, so it's. This is, looks like function calls or function pointers. Huh. Yeah, this is super weird. So why is it doing D word plus, I bet, so we'll see some kind of weird, sub push call EAX, right? So that's what gets thing there. So it goes in there. I don't know why IDA can't determine that, although maybe, does that set that up there? No, returns result. Huh. Okay, so where is that set up then? Hmm. That is used in RSA import. Okay. So, don't really know what's going on here, but this is again one of those cases where I don't get too bogged down here. We can see that we're passing in here the pointer to the digest, digest length, some v2 value, which is the buff size. That's a size of digest length. The address of digest length 1, 0, and RSA key 1. Okay, so we're going to do some stuff here. If the lengths don't match, then assertion failed. So the two digest lengths. So this must write out the input of how much it processes here, is my guess. That's why you would pass in a pointer. And then, okay, so V20 is buff size of digest length. So if that or if that bracket 1 is equal to 0, it's not equal to 1. Okay, so this is like looking at the digest, it looks like. Doing it in a weird way. The 29 is 0. I is equal to 1. Ooh, that's weird. I is equal to 1. I is less than digest length 1. I plus plus. If buff. Oh, if not, V9 is equal to I 0. Oh, because we just checked 1. That's weird. I wonder if this is some crazy optimization. Oh no, this checks bracket 1, not 0. I don't think 0 is being checked. So is it something like maybe it's some offset where the first byte of the digest isn't being checked, so you could maybe brute force something that worked there? I actually don't know. That's interesting. Okay. That is definitely a 1, right? Yeah. Okay. Buff size of digest length I. If not. So if it's not 0, then set that equal to 0. That is 0. If 0, then it's true. Okay. I'm not really sure what's happening here. And this is another thing where, you kind of, if you're spending too much brain power getting the details here, but it does look funky. Just going to note that. Okay, if not before, then assertion failed. Otherwise, then V29 is the address of this plus 1. This is so weird. Okay. That V11, it's just like is, which is a buffer of 4 ints. Set those ints up. V12 is equal to 1024. Okay, J is equal to 0. J is less than or equal to 12 hex. J plus plus. If V19 J is not equal to V byte J1 plus J. Oh, interesting. Okay, so this looks like it's the. Okay, so 4. So what do we say? So a SHA-256 hash is exactly 12 characters. Then, sorry, is 32 characters. 256 bits. 256 divided by 32. That would be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's weird. Then it sounds like this is a SHA 512, maybe? I don't know, because it's comparing these bytes, right? So that's what it's doing here, plus J. So yeah, it's basically like mem setting this to be these fixed values. Okay, which makes sense. That's why we didn't see any of these values there. This V12 is doing, or why V13 is being set here. But okay, verifies that these pass. Oh, 12. Let's decimal 18. So 18 bytes. So we'll go, wait, 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16. Wait, 17, 18. Oh, okay. So this V12 and V13 is BS. This actually is not used anywhere or anything. So the way we can fix that is we're going to call this a character array of size 18. Yep, we're going to overlap with variables. I think that's fine. Sweet. Okay, so why does V12? Oh, less than or equal to 18 means it's going to do one more, right? Oh, God, that's so annoying. Okay, so it's actually 19 bytes of whatever the hell this is. Why didn't I get that there? Oh, 19 bytes. Oh, yes, I do want to do that. Okay, so this is it's comparing 19 bytes of whatever the hell this digest is. And then it is comparing those with whatever is the output of this thing. And then it says V17 plus 19. Okay, great. So that makes sense. We just said it is those 19s into here. Then it says 24 equal to 1. If k equals 0, k is less than or equal to 31, so 32. If k is not equal to hash output. Ooh. This is an HMAC or something? All right. So we're getting some idea of the structure here, at least. So we know things about this buff that's being created here, that's getting passed all the way here. So this function here is like setting up this value here in such a way that the first value means something, but then the next ones is like looking at the state. I don't know. This like 19 is super weird thing to happen here. And then finally, it's saying that this V16 is the signature digest. Okay, so to break this stuff, we'll need to do that there. The other things we've at least figured out are what are the platforms. So I think I'm going to stop here. I've been doing this for a while, apparently. And so what we'll do next is start from here, start to look at and reverse engineer the Ruby code. Maybe there's some cool bug in that functionality of the application that we can execute, and maybe that's what allows us to do crazy stuff with this payload here. So cool. Hope you enjoyed hacking with me. I know it was fun for me. So I will check y'all next time. I don't know. I'm going to do this a lot more frequently now. So be on the lookout. So thanks, everyone. Bye.